And then he realized that every day Noah recompile the adjustments for the station records. And every day, those adjustments are different for a lot of the stations.
My guest today is Ronan Connolly.
So we're talking here about the role of the sun in climate change, which is a long-standing topic. It's been going on for pretty much since before the IPCC was founded. That's the UN Intergovernmental Panel on Climate Change. But when they were founded, they didn't actually consider the role of that possible role of the sun in climate change. And then that was in 1990. With consecutive reports, they grudgingly said, well, let's put back in the sun. But there's been this battle where each report, they had to concede that the sun is important, but they've been trying to make it say less important as we've gone along. Now, we just have a paper published in the Astrophysical Journal on the total solar irradiance changes in the satellite era, which is just from 1978 to present. But this will have implications for the entire looking at longer from 1850 up to present. So some of your viewers, Tom, might have heard some of our previous talks. So I think was it last year, my father, Michael Connolly, and our colleague, Dr. Willie Soon, we had a three-way presentation where we were each presenting different aspects of this problem. At that, we were talking about these four papers that we've published. So in this talk, I'd like to talk about our latest paper looking at the satellite era, but I realize not everybody will be familiar with the context of it. So maybe I should just give a summary of what we described before. Does that make sense?
That makes a ton of sense. Let's do that. Yep.
Okay.
Yep.
Okay. So first off, why do they say global warming is mostly human caused? And so everybody's heard this. A lot of your listeners, I imagine, are familiar with the Intergovernmental Panel on Climate Change, the IPCC. If you're not, then anytime you hear the UN has said climate change is due to human-caused activities, then that's what they're referring to. It's a joint body in conjunction between the World Meteorological Organization and the UN. So they say that global warming is mostly human-caused, and this is why they do it. So what they do is they get their computer models, their global climate models, GCMs, and they do a retrospective simulation of how the climate should have changed since 1850, for instance. And then what they do is they compare it, they run their simulation with just natural factors. And so this here is their hindcast. So it's the opposite of a forecast. A forecast is predicting what will happen in the future. And a hindcast is figuring out what happened in the past. And so what they do is they get their computer simulation to simulate what should have happened. And they run it using only natural. And then they rerun it using what they call their anthropogenic or their human factors. And they get this beige color here. And then this black line is their observed temperature record. And so they say, look, up until, say, the 1950s, the observed temperature, it kind of fits into both. But from here on, you cannot see, it doesn't fit the observed. So they say, since 1950s, global warming must be mostly human caused. Does that make sense to you, to what their logic is? You don't have to agree or disagree.
Well, yeah, it does make sense. They're telling us that, but I have no faith at all in that simulated natural thing. Zero faith. And there's this narrative that we know that humans caused it because temperatures shot up with the Industrial Revolution. But that's not at all what this shows.
Yeah. Well, yeah. So we'll talk about this in a bit more detail, but let's just go on to, a lot of people, you may have seen, Tom, have you seen this graph floating
Many times,
around?
yep, I have. Yep.
Yeah. If you Google what are the causes of climate change, one of the top ranked pages is NASA, climate.nasa.gov. And everyone's like, well, NASA, they landed us on the moon. So these guys must know what they're talking about. Nobody in climate.nasa.gov was involved in the moon landing. Okay, NASA is a large organization. There's thousands of employees. I've talked to quite a few NASA employees off the record, and there are NASA scientists off the record that don't necessarily agree. But I will say that there are NASA employees on the record and off the record who believe in this narrative. But it's a group of people. If you get thousands of people, you're going to have a different views. But the people who designed this graph, this is they believe compelling arguments. So what they have here, these aren't computer models. They're just comparing. The red is the NASA GISS's global temperature record, and the yellow is an estimate of the total solar irradiance changes. And you see the way that they're going up and down, and this keeps going up and this goes down. And so they say, so again, up to here, maybe it could be due to the sun, but after, it's not. That's what they say. So this graph appeals to a lot of people.
By the way, I don't believe that red part of the graph at all either. Not at all. Every single recent year for decades has been warmer than the warmest year in the 40s.
Okay, so we'll talk about both graphs simultaneously, but just to summarize, you have the model-based attribution analysis. So that's the one that the IPCC does. It's a bit more sophisticated. So I have to be clear, the IPCC claim they do not do any research themselves. They just compile the research. But as part of the IPCC project, all of the climate and computer modeling groups around the world, they contribute through this project, which was called the CMIP6 for the last report. They contribute their hindcasts, and then the IPCC looks at, they do that graph, and they say that's it. So they say, it's hard to know. On one hand, they claim they're not doing research, and then on the other hand, they say, but here's some research we did. And okay, the other one is, it's literally just comparing a temperature record with a TSI record. So we'll talk about both of them. First one, how reliable is the global temperature record? And so the global temperature record, this is the instrumental one. And maybe we could talk about proxies and another thing, but none of those graphs were on instrumental temperatures. And so there are two parts. You have the land component, and then you have the ocean component. The land is made from weather station records from thousands of stations around the world. Sounds impressive. And it's somewhat, we'll get into that in a second. The other is sea surface temperatures. For most of from the 19th century up till the 1980s, it was almost all based on ship measurements. Two ships pass in the middle of the night, and one of them puts throws a bucket out and takes a sample of it. That's what they're doing. I'm just kind of simplifying it, but they're taking ship measurements mostly. Then in the 80s and more recently, we have weather buoys. There's problems with both, and we've mostly focused on the land, and we'll mostly talk about it. But let's get into the land component. The biggest problem is what's called the urban heat island. Now, most of if you haven't heard of the urban heat island or you don't know what it is, if you have a car and there's a thermometer in your car, next time you're driving into a city or out of a city, have a look. You'll probably notice as you enter into the city that it gets warmer and warmer. Just, it may be a degree, maybe 2 degrees, a couple of degrees. Then when you leave, it gets colder again. That is called the urban heat island. Its cities are warmer than the surrounding countryside. Now, technically, that's human-caused climate change. We are causing climate change, but urban areas only account for 3 to 4% of the land area. And because there's more oceans, it's only like 1 to 2% of the total globe. So if you are using urban stations for sampling the temperature, you're not sampling the globe. You're just measuring urban climate change, not global climate change, right? And now that's urban climate change is important. Like since 2011, more than half of the world's population lives in urban areas. That's the UN estimate. They do these estimates of who lives in urban and rural, and looking at the population growth. Since 2011, they said more people live in urban than in rural areas, and urban people living in urban areas are indeed experiencing human-caused climate change. And like whatever you think about global temperatures, we can get onto that. But if you're living in an urban area, 100% I can say that the climate changes that you are experiencing are unusual. But like, if you're interested in global climate, then you have to get outside of the cities. Does that make sense?
Totally. Yeah, it does.
And this is just, I find this is from noaa.climate.gov, and it's a nice map. This is a heat map of Washington, D.C. And you could see the area here. You could see, I don't know if you could see, the green areas are cooler or whatever. And interestingly, if you look at the voting records for people living in Washington, D.C., they have consistently been voting for the party that says that we are seeing unusual climate change, which in your case is the Democrats, yeah? And it's so they are experiencing human climate change more than outside of DC, which is what they're saying, urban climate. And so here's a problem for our global temperatures. If you have a weather station that when it was set up, it wasn't so urbanized. By the time it becomes urbanized, its record will show the natural climate change from outside, but it'll also show this extra little bit of warming that comes from the urban area. And this is very difficult to calculate, but this is looking at the NOAA's Global Historical Climatology Network, version 3, which is their older one, their older data set. But it's the one that we did most of our analysis on. And so they included in it estimates of both the night brightness associated with each station and the population density with each station. So for version 3, they dropped that. They said, oh, we don't need to worry about urbanization, which was a mistake in our opinion. And so we're working on trying to analyze their version 4 stations. Now, that's ongoing work. We can talk about that later. But you can see here, first thing, this is looking at the number of stations available for 1880 to 1910. So for 30 years, and these are the stations that have the data for that 30-year period at the end of the 19th century, early 20th century. So the first thing you might notice is there's very few in the southern hemisphere. Am I right? Does that seem? Yeah. Now, modern era, we've lots of stations in the southern hemisphere. Yeah. But if you want to look at temperature change since the 19th century, you're mostly looking at the northern hemisphere. And we've been pointing that out. We're saying we haven't been able to comment on the long-term trends in the southern hemisphere because of this problem. And so we keep on saying we're in our papers, when we're looking at the northern hemisphere, we're looking at the northern hemisphere. And then you'll get people saying, well, these group are looking at the global temperatures. They must be better. It's like, yeah, okay. They can say they're looking at the globe, but does that mean that they're actually looking at the globe? So the other point is that most of our longest and best kept stations are urban. Now, they weren't urban in 1880 as they are now. That's the point. If you want to look at the temperature trends from continuous, I'll just show this in another way. This is the stations available in 1850. And we're looking at how urbanized they are now. The same stations. Only 5% of the stations are still rural. The stations that were available in 1850, 71% of them are now highly urbanized. And you get others that are partially urbanized. Okay, so think about that a little bit more. You know, you can see, so this is a bit a counterintuitive thing. People say urban heat islands are greatest for it's now it's the greatest. Yeah, okay, so it's urban heat islands are growing in most recent decades. But that's not the problem because we actually have a lot of rural data. Yeah.
Oh, I'm curious, how many stations do we have that have been around since 1850? Any idea what that number might be globally?
Yeah. Do I have it on this slide? I was trying to avoid complicating it too much. I did have it on the slide, but I didn't want to give you too much information. But like 1850, it's mostly just Europe, and some North America. Actually, 1850 is mostly just Europe and a few in what was part of the British Empire. You had some in like India, and then you had some in East Asia as well. You had a handful there. By 1895, I don't know who the U.S. president at the time was. It maybe Grover Cleveland or someone. I don't know. He said we need to start monitoring. So he started this program that's called the co-op program. And so there's a large number of stations for the contiguous United States that have records going back to 1895 from across the whole country. So for the US, there's a lot of stations from about 1895 onwards that are rural. But outside, you know, we're talking, yeah.
Oh, just one more question. Central England temperature record, that's maybe the longest running instrumental record. Do we have a number of other ones that are up there that are anywhere near that long, or that's totally an outlier?
It's the Central England temperature record that was developed by, I think, Gordon Manley in the 50s up until the 70s. It's not actually a continuous record. So what he did is he took some different weather stations and from around England, and he just kind of, it's a very interesting record. Unfortunately, as he pointed out, most of the stations that he was using had become urbanized. His last update was in 1970. Then it was updated by the I think the Climate Research Unit in England, and I don't think that they have adequately corrected for urbanization bias in the later period. But even with the Central England temperature, you have to be cautious because Fahrenheit scale was only invented in 1740 something, and that record goes back to, I think, like 1600s. They're using, it's kind of a documentary based proxy record. It's not like a strict temperature record, even going back that far, but it is a very good one. But there's even a period when Manley said he had no English temperatures. So he went and he said, but I have some, I think, Dutch records that he could use. So for like in the early part, there's like, I think a few decades when central England is actually in the Netherlands or something like that. So that's the longest continuous instrumentally based record is the central England temperature. And then there's some other records that start like Hohenpeisenberg is it Germany? I think it's Germany, maybe Austria. I think it's Germany. Hohenpeisenberg goes back to the late 1700s, and that's also quite rural. You have Bonn. The Bonn record, I think, goes back to 1700. So there are a few, but that's a highly urbanized station. Okay, so keep the question coming. But another problem, and this is another controversial one, that some of your listeners, I imagine, will be saying, no, this is dreadful. And then others will be saying, no, this is perfectly good. So this is called the temperature homogenization. And so a lot of the groups, they recognize that there are non-climatic biases in the temperature records. Well, since like the early 2000s, even like late 90s to early 2000s, groups started developing statistical homogenization computer programs, computer algorithms. So currently, NOAA use Mene and Williams pairwise homogenization algorithm that was developed in 2009. But there are other similar, we've written a couple of papers on this. The idea is what they will do is they will take each station record, weather station record, and they will compare it to the weather stations from nearby neighboring stations, year by year or month by month, and they'll say, oh, this one's going up, this is going down. And by doing this statistical comparison, they will apply adjustments to each station up and down at different points. And they say that those adjustments are correcting for non-climatic biases. And the problem is, what you end up with a homogeneous mix. So homogenization works. If you take homogenized milk, I don't know if people are familiar with the word homogenized, but that's what they're doing. They are bringing everything to show similar trends. So in 2022, we did this collaboration with a lot of European scientists some of them from the meteorological groups. And by the way, this is a collaboration with different people. And I need to stress that a lot of these scientists, they agree with homogenization. They agree with the IPCC. They don't necessarily endorse all of the views that I have or my colleagues will have. But that's the point of when you're doing good science, you don't have to agree with your co-authors on everything. But we agreed with everything that was said in this paper. Okay. And that's the key bit. All of the co-authors agreed to what we found. And what we found is we took NOAA's homogenization adjustments that they had applied to each temperature station that we had. Each of these groups had looked in the documentation for what are called station history metadata. So that's where the station observers would said we had to move our weather station because there was a building was about to be put up around it. And so they said, so we've moved it 100 meters here, or we've changed the old screen was out of date. We've replaced it with a new one. We've replaced this. So they have recorded, a lot of these observers have recorded major changes that took place at different times of the record. And we said, okay, can we get that? And we had it for more than 800 weather stations from 24 European countries. I don't know, can you see all of the red dots? They're the stations that we got weather station, the station history metadata from observers from them. And the white ones we didn't. So we just analyzed the 800. What we noticed is, this is our colleague, Peter O'Neill. He's a retired engineer, and he downloaded NOAA's homogenized data set, I think by 2011. It was the first time he downloaded it, or maybe 2010. You can check the paper. But he started, he went back to check the adjustments that had been done to a weather station. And he realized that the adjustments had changed. And a few months later, then he went back and he said, okay, and then he realized that every day NOAA recompile the adjustments for the station records. And every day, those adjustments are different for a lot of the stations. And they shouldn't be. If they're correcting for, like, say, oh, there's the station, there's a warming bias of plus 0.5 degrees in February 1957. Okay, that's great. But then the next day, they rerun it and say, actually, it's a cooling bias today. Well, it shouldn't be. So what we did is we said, let's just check, first of all, how consistent are the adjustments? And what we found is only 17% of their adjustments remain consistent from day to day. For a given, you download the homogenized record, and only 17% of the time does that stay the same. Each time you download it, it'll be different. And then we said, well, how many of those adjustments actually correspond to a documented station history event? 19%. Okay, so does that make sense? Well, do you get what we're trying to say? We were shocked, and I can tell you, all of our co-authors were shocked, and they all, I said that they all agreed with the IPCC and all of that. Quite a few of them said to me, we might have to look at some of our assumptions again, but I don't want to put words in their mouths. We did this other paper. This is last year. Was published in an AMS journal, JAMC, and it's called Evidence of Urban Blending and Homogenized Temperature Records in Japan and in the US. I don't want to get too long because I know we're talking on for quite a bit. I know we've quite a bit to go. But this is basically what we found is, do you remember is saying that it homogenizes, the algorithm homogenizes. What we found is that it's like if you have strawberries and bananas and you put them into a blender and you blend them, at the end you get a nice strawberry banana smoothie, and it can be nice. But what you don't get is pure strawberries or pure bananas. You get an average of the two of them. That's what happens. If you put urban station records and rural station records into their homogenization blender, what you get at the end is the urban records go they go down a little bit. That's fine. You can remove some of the urban, but the rural goes up. And then here's the genius that a lot of people don't have came up with. They said, oh, now let's compare the difference between the rural homogenized and the urban homogenized. And then it's like, wow, most of the differences are gone now. And it's like, wow, the blending seems to have worked. And that's a problem that we've been telling people about that is not correct. So we've been telling about this for more than a decade now. But we just said, look, can we go and do it? So this was starting in 2015, and our last update was in 2019. Or we did it in 2021. But they remember the GHCN version 3, they was discontinued in 2019. So we can only do it up to middle of 2019. So we can only go up to 2018. And what we did is we said, can we identify regions where we can have information about the stations and only use the rural stations, or stations where we can correct for urbanization bias, or we had station history information. And these are the 4 regions. Now, one of the people, a lot of what criticism we'll often get is, oh, but why didn't you use everything? It's like, well, we need to have information about it. You get a lot of these stations, rural stations, that have like 10 years of data and then a gap of 50 years. And then it's at a different thing. And it's like, what happened in between there? If you don't know, and they don't know, they don't tell you what happened, then how can you know whether that was climatic or whether that was the weather station was moved to a uphill or downhill or something like that? So we wanted to focus on ones we had information on. But it says, oh, these are just 4 regions. Well, yeah, okay, there was some data we didn't have. So just using these 4 regions, you can see that we have more than 90% of all of the rural, this is in the Northern Hemisphere, because remember, there's very little for the Southern Hemisphere. So we actually were using those 4 regions account for most of the temperature records around here of rural. Does this graph make sense? What I'm doing is, this is the percentage of the Northern Hemisphere rural data available for each year. And this is the ones from our 4 regions. And these are the ones that were outside of those 4 regions. Does that make sense?
I am not quite getting it there. What is the, you right above your cursor there? What's the 90% mean again?
Okay.
Yeah.
These 4 regions here, we just focused on those. We did a detailed analysis. We said, okay, we've analyzed these ones. We have information about them. And we want to get more information about the other. But in the meantime, let's focus on the ones we know. These are the longest records, best kept that we have information about. And then we said, okay, but you can see there's regions outside here that we didn't include. We said, let's just focus on the bits we do know. And then it's like, well, actually those 4 regions happen to be most of the temperature rural data that's available for the early 20th century. Now, it's only half of the data for the 1970s. Okay. So, yeah, we could improve the data here, but we're interested in the long-term trend. So it's not perfect, but it's like, we realize you can't use the homogenized data, and you can't just randomly, you need to get station history information to correct for it. So anyway, that's our rural record. So how does it compare? This is the Northern Hemisphere using all stations. You can see it going up here, right? This is our estimate using only those, only the rural stations for those regions. Now, we did analysis as well. We do a comparison in the paper where we compare the urban and rural for those 4 regions. We do all of this stuff. We compare to others. So can you see the differences? Now, for me, these are very different, but I just go to, okay, what we're finding here is you could see warming, a very slight cooling from the 40s to the 70s, but then continuing going on. Not really much of a change. What we find here is warming from the end of the 19th century, which was, as you know, the end of the Little Ice Age, up to the 1940s, and then cooling from the 40s to the 70s, which maybe some of your older listeners might be familiar with. I was born after this cooling, but there was a global cooling scare in the 60s and 70s, where people were noticing the temperatures are cooling. Then they started warming again, and everyone said, oh, we'll change our mind about that. But what we're finding here is, yes, it's warmer than the end of the 19th century, the Little Ice Age, is warmer than the 1970s, the end of the global cooling period. But it's not this continuous rise that you see with the urban and rural. It's more cyclical. You have a rise, fall, rise. Does that difference make sense? Now, look, it's not a perfect analysis. It's the best we have. None of the other groups are doing a rural land using unhomogenized data. None of the other groups are doing that, using unhomogenized data, without using this blended data. All of the groups are either using the blending or they're doing, and so this is the best estimate of Northern Hemisphere rural land temperatures that's out there. And how does it compare? Oh, the IPCC, they said no recent literature has emerged to alter the AR5 finding that it is unlikely that any uncorrected effects from urbanization have raised global land surface air temperature trends by more than 10%. And therefore, we don't need to worry about it. Now, I actually argue 10% you should be paying attention to. And also, notice that it's not a linear trend. What we're finding is in the rural data is showing more of a cyclical. So people looking at linear trends, it makes sense if you're looking at the urban data. Okay, but now onto the sea surface temperatures. Now just showing you here, this is just a graph for ocean heat content surface measurements. Sea surface temperature is slightly different, but this gives you the same point. First, this is in 1955. First, Southern Hemisphere. Does this make sense? This is where they have at least one measurement, 2 to 5 measurements, more than 30 measurements for that year. Now, I don't know about you, but I don't think that the Southern Hemisphere had much data, yeah?
Right.
Okay, so again, we have Northern Hemisphere, but not so much Southern Hemisphere. The other problem is that this is from John Kennedy et al., 2019. Again, he doesn't necessarily agree with me on a lot of the stuff, but this is quite a reasonable analysis. And he's working for the Hadley Center. And again, pointing out that there's changes in the types of measurements that are being done. First of all, again, these are the number of observations that go into the thing. And you can see that's 1,000 observations. So comparing 1890s to modern day, there's huge difference. We can say with far more confidence, we know a lot about what's happening since the 1980s onward. But when you're comparing now to the past, you're getting into problems. And here is what you can see is that from the 1980s to present, we've had more and more buoys. But before we were using buckets, and then we were using engine room intakes. And this is the other thing that's what Kennedy et al. Did is they took all of the parallel measurements from the engine room intake, and then they took all of the bucket measurements and they calculated the temperature trends using both, and they found different trends. They converged towards reason. So how do you know? It is a bit of a mess. And Kennedy et al. Are doing the best they can, trying to do it. But it's like people saying, oh, the sea surface temperature, no urbanization bias there. That's true. But you have other problems. So anyway, just to wrap up, we have here, that's our rural record. Here's, again, Northern Hemisphere. Now, this is the sea surface temperatures. And they're not that different. Are they? You're seeing similar. You have the cooling, warming, cooling, warming. The magnitudes are different, but like they don't look too different to you. Tom, what do you think?
I agree.
Like,
They look kind of the same.
yeah.
Yep. Mhm.
And interestingly, here's tree ring proxies for the Northern Hemisphere. And again, you find you don't get the cooling at the start, but you do get the warming. Peaks a little bit later, more like the 50s instead of the 40s. Then cooling and so, and it finishes in 2000. Glacier lengths, you're getting similar patterns occurring. And again, even weather balloons. The problem with the weather balloons is we only really have data from about 1958 that we have global coverage, and the satellites only from 1978. So yeah, we're saying this rural record is consistent with the tree rings, sea surface temperatures, glacier lengths, qualitatively, weather balloons, satellite, ocean heat content, and that, so maybe this is correct. So
Yep.
no, yeah. Okay, we go back.
Can we go back to that tree ring one? Are we seeing the decline thing in the 1960s there? Is that it or no?
This group, this is like compiled from some of the best ones that have done efforts to, like, there is this height to decline problem. Part of the height to decline problem is that they're not showing the urban heat island. But other ones are that they actually are showing a stronger cooling. These were the kind of the best estimates that were around, the average of the best of estimates that were around when we did this paper in 2021. Some regions have this decline, other regions have. We could get into a whole other discussion on this because there's problems about tree ring standardization. You know, where you have things like when a tree is growing, the growth rate is different for young trees than old trees. So when you are trying to account for that, you need to apply an age-fitting model. And there are different age-fitting models. And so by playing around with them, you can get different results. There's a lot of different issues in there. There's some good scientists working in it. There's some less good scientists working on it. And I prefer these records for now. Again, we could talk about proxies maybe in another podcast if you want.
Just one more thing. I'm just not seeing any sort of a blade in that tree ring proxy there. There's no blade.
Yeah, that's it. Well, we need to. That's the reality. That's the Northern Hemisphere tree rings, and the Southern Hemisphere, they don't really have many. They don't really have the blade either. Look, you have to be very constructive, imaginative to create your blades. But I know there are scientists out there with good imagination that have different techniques that they can use for creating a hockey stick. Okay, we've been talking a good while, so stop me if I'm going on too long, or if it's going off. But we're still going back over stuff that we've done. So if you recall, the start of this talk, we were talking about how you have to observe temperature records, and then they were saying, like the NASA climate website and also the IPCC, they said, when we compare it to the natural forcings, they diverge from about the 50s, 60s onwards. Okay, well, how do they calculate TSI, total solar irradiance? Well, before they put, this is Akron 1, before they launched the first satellites in the 1978, there was no way of directly measuring it. I'm simplifying. We could go in and like if you read the papers, there were attempts The Smithsonian, the Astrophysical Observatory, they tried to record from the ground, but there's so much noise. If you're trying to measure solar input from ground, you're not measuring the solar input, you're measuring what's left after you get through the atmosphere. So really, if you want to see how much solar energy is arriving, you have to get above the atmosphere. So that takes satellites. So that began in 1978. And we'll talk about that more. That's the focus of that paper that I've mentioned that we just had published. But before the satellite era, you have to rely on solar proxies. And that one of the ones that everyone's obsessed with, and there's reasons for it, is what's called a sunspot number record. If you want, you also have cosmogenic isotope records, beryllium-10, carbon-14. They can give you the long-term, multi-decadal changes, but there's contamination with some of the data from the mid-20th century onwards. So they're really, really good. They're best for looking at long-term changes from centuries to centuries. Now, so the basic idea to construct TSI from 1850 to present, for instance, which is what the IPCC were using, is you get your solar proxies and you combine them maybe with a model, a theoretical model, or maybe just simply fitting it with the satellite data. And then, so there's lots of ways you can do that. So in our first paper on this in 2015, we actually found, there's actually 8. We found 8 different reconstructions that the IPCC could have considered. And then we said, but they only considered 1. And we said, well, and then why did they do that? And then we noticed actually if they'd considered some of the other 8, they wouldn't have reached the same conclusion they did. In our 2021 paper, which you can see we had a lot of co-authors on this paper, and several involved in temperature TSI reconstruction as well. Doug Hyde, and we had Nicholas Caffette, Richard Wilson from the Akron team. And just to mention a few, we had John Butler. For that paper, we said, actually, we found another 8. We had 16 reconstructions they could have used. And then the IPCC, they were saying, we're only going to use 1. We say, that's not going to help. And then after the IPCC published, they only used 1. So in a follow-up paper that was published last year, we found even more. We got 27 TSI reconstructions that covered 1850, at least 1850 to present. And this is a big mess of a thing. This is all 27 of them. I don't know if you can even make out the writing on it. You can read our paper. You can download all 27. We have that. We've made that available for everybody to access. But you can see this is one, this is another. Let's see if I can find, let's see. This is the one the IPCC used for their 6th assessment report. And now they won the NASA climate used Satire T2. And we didn't actually do that one here. We just did Satire. We did 2 of the Satire. This is Satire M. Oh no, sorry, that's Satire M, and this is Satire T1. So those are the things. Okay, they look similar, but you can see there's lots of different ones. Now, we're not the only ones that have been looking at this. This is Theodosius Chatsistergas et al. I hope I have his name pronounced correctly. He apparently hates me on Twitter. He just keeps on. Anytime anyone shares any of our papers, he goes and starts doing big long rants saying, how dare you, how dare you. Fine, I haven't met him yet. Maybe he's a nice guy offline. I think a lot of people online, they maybe a different personality. Anyway, I tried to have discussions with him. Well, you can have a look on X, and I'm open to having constructive discussions with him. But in the meantime, he had this paper. He led this one with the MPS group. Now, the MPS group are the ones that developed the satire TSI reconstructions. But they did this paper in published the same time as our 2023 paper. We both published around the same time. So they had gone and they calculated, they found 32 reconstructions, and 18 of theirs overlapped with ours. So when you add them all between us, we've identified 41 different reconstructions. Now, I have to stress, they say often older versions are used in the literature, ignoring the fact that newer versions overriding the earlier ones are available. We caution against using outdated reconstructions. So they think this is science, and we think that's what's called appeal to novelty. It's the argumentum ad novitatem, which just because something is newer doesn't mean that it's better. And we think we should look at all of them and see them together. But so this is their figure 4, and they are saying they caution against using the older ones. And they say we should be just using the more recent reconstructions. Now, Tom, just as somebody that maybe is not into all of these TSI, they're saying scrap that. It's not at all like that. This is what it's like. So can you see a big difference between the two of them?
A lot of stuff going on in the 1700 area, the more recent ones. That big difference.
Anyway, apparently, just it. So when they say this is really bad, this is not so bad. That's according to Chatzister-Goss et al. 2023. So there you go. Okay. He also has written a solo paper specifically attacking this one reconstruction that was published in 1992 or 1993. Now, he says he has updated. This was a very important paper because it's one of the few reconstructions that's tried to calculate different solar proxies, not just sunspot numbers. And, they tried to look for as many different estimates of solar activity as they could, but they were very limited in how much data they had, and a lot of the records were older. So Chatzister-Goss says that he has managed to update them, and then when he recompiled it, he gets this, and he says, "Oh, look, that's the update." Now, I don't think that's an update. What we call it a remake. So we haven't published anything in the peer-reviewed literature on this because we have other things to do. But we've written a detailed analysis on the series website, which the website reckons it takes 51 minutes to read. Okay, if you're interested, I definitely recommend reading this post. And what we found is basically, look, Disney have gotten very into doing updates to old films. And, maybe some of them are better. But I think, look, they're remakes. That's the best way to do it. It's a remake. So this is his remake. But what we did is we said, look, if it was genuine, what you would do is Hoyt and Shatton have been very careful to say, we're not just putting them all in and scaling them to match, the satellite in this thing. They had taken considerable care to try and incorporate the multi-decadal trends. So what we said is, look, if you actually were consistent, then using the extra updated data he collected, and this is what we get. So this is using his Chatzister-Goss's data, his extended updates, but applying Hoyt and Chatton's actual methodology and philosophy. We get this result, right? So there's the remake. And then here's the other thing. Hoyt has told us that Chatzister-Goss emailed him, said, oh, I want to do this. And Hoyt tried to have a constructive dialogue with him. He's a nice guy. He's like interested in science, but everything was just being, he found it very frustrating. He said, why are you using this? Look, if I was doing it again, I would do this. He was making the things and he was just ignored. Like, I don't know. Anyway, so I'm not endorsing this as a reconstruction. I'm just saying, if you were to use Chatzister-Goss's extensions of the data, which Hoyt has not endorsed, in fact, he specifically disagreed with several of his the Chatzister-Goss's choices. That's what you get, which is not that. So, and interestingly, Chatzister-Goss is like, he doesn't even seem to say that this is a TSI reconstruction. Anyway, look, let's just compromise and just talk about the ones that are the recent reconstructions. So I've just taken 4 that are in common to the two of us, that are in the recent ones. And this is the one that the IPCC AR6 used. This is SAT-IR-M. It's similar to SAT-IR-T2, so it's similar to the one NASA climate. There's a slight differences here, but these are 2 other ones that I've taken out of the 20s, out of the 41 reconstructions, but out of the ones that are modern. There's different stories there, right? Like, what am I wrong in just thinking that these might suggested if the IPCC had plugged this one in, would they have got a different result? Maybe. If NASA had climate had done it. Okay, so why do you get all of these different reconstructions? Well, first is, a lot of them are using the sunspot records. So, but sunspot records are not a direct measurement of TSI. So let's have a bit of a discussion. So a lot of people get confused about what the difference is, and they just say sunspots are TSI and everything. It's like, so what is a sunspot? So at the time of Galileo, and he wasn't the first, but Galileo is the most famous, they pointed their telescope at the sun. And I have to stress, don't look into the telescope at the sun unless you have a specific UV filter on it. But if you take you point it at the sun and you shine the lens onto a card, then what you could do is you can sketch an outline of the sun, and you see these dark patches. And that's what they did. And these are called sunspots, the dark patches. So this is John Briggs. He actually physically made this? I found this online, a nice photo. He physically made an 18th century telescope and put a card to show how you could record it easily. You can just point out at the sun and record it. So does that make it just that? Had you known about that? And you could just see, it's like, there's a lot of features in there. There's dark patches, umbra, penumbra, and there's groups of sunspots. So there's a lot of, it's not just spots. But in the 1840s, there was like Schwabe decided to record sunspots, and he did that for like 17 years. And at the end of it, he said, hey, there's this pattern where the sunspot numbers increase for years and years, and then they decrease, and then they increase again. And he said it's like roughly 10 years, but he had only 17 years of data. They just say maybe 10 year was a nice round number. So Rudolf Wolf, he went back, collected all of the data back to Galileo, and he said, yeah, actually, all that he could find, he said that there is this cycle. It's an average of 11 years. Sometimes it's shorter, sometimes it's longer, but it's roughly 11 years. So the Schwabe cycle is now called solar cycles. And we had good data from about 1760s. So we actually call that solar cycle 1, 2, 3, 4, 5. So when you hear solar cycle 24 has ended, then that's what they're talking about. We're now approaching the maximum of solar cycle 25. And that's it. Now, just to show you, these are the cycles going back. Sunspots numbers. Hoyt-Schatten in 1998, like that's different from the Hoyt-Schatten 1993. A lot of people get those two papers mixed up. In 93 paper, he'd been looking at a sunspot record and said, this is very chaotic. He had problems with it. There was a lot of inconsistency. But he said, actually, if you just focus on the sunspot groups, there's a lot more consistency on the sunspot groups. So he developed the group sunspot numbers, GSN, and that was able to go back to 1610. And one of the things that jumps out of it actually was, he wasn't the first to do it, but you had this Mulder minimum when there was almost no sunspot activity, and then another period of the Dalton minimum. But what was the relationship between the sunspot numbers and TSI? That's a good question. And that's one that is ongoing, and you'll hear people conflating them together. And this is a big problem because it's not so simple. So before the satellite era, you couldn't tell because we didn't have the direct measurements of TSI for long enough to see. So that's one of the big things they said. When they launch a satellite, what's going to happen? Will TSI go up or down? Because one argument was sunspots are dark. So when you have more sunspots, then the sun is going to be darker, less bright, so there'll be less TSI. Does that make sense?
Yep.
Yeah? Okay, but then there was another argument that said, well, hang on, that Mulder minimum was since you're in the Little Ice Age. It was really, really cold. So you had almost no sunspots, and yet you had one of the coldest periods of the last millennium. So they said maybe actually sunspots increase TSI. And yet, of course, until you measure it, maybe they're independent. So we have three competing theories for how, and they're all plausible, right? Would you agree that they are before you have observations? So what happens when we get observations? Okay, 1 year of the first year of Akron, I'm focusing on Akron 1. There was the Nimbus 7 started in 1978, but Akron 1 started in 1980. 1 year of data here. So this is the TSI measurements, and these are the sunspot numbers. Now, do you notice here, when there's a big sunspot group passing, and I've shown 3 examples here, you get this big drop in TSI. So do you see that?
Yep.
So based on 1 year of data, we can see actually the more sunspot numbers you have, the lower TSI you have. So which of our theories is correct? Theory 1, yeah? More sunspot numbers, lower TSI. Brilliant. Resolved. What about 10 years of data? Oh, okay. When you see here, we have our solar cycle, the sunspot cycle. When the sunspot numbers got lower and lower, TSI also got lower and lower, and then it gets back up again. So when we have 10 years of data, it's reversed. We actually have the more sunspot numbers you have, the higher TSI is. Okay, so what's going on here? Right, this is the problem. And then, that would say you have 1 year, it gives you one result, 10 years gives you the opposite theory. So here, this is a month of a spacecraft, or the NASA SGO spacecraft in 2014. This was near a solar maximum in 2014, I think April. You can see these sunspots here. This is the HMI intensity. It's looking at the magnetic behavior. So can you see these sunspots? Yeah.
Yep. Yep.
Okay. So you're focusing on there. Now, here we're using a filter, 17 angstrom filter, and this captures the photosphere, but it captures a lot of the bright features of the solar sphere, of the photosphere. So if we look back at it again, do you see around each black spot, dark spot, we have white areas. These are faculae, which Latin for torch, and you also have plage areas. And you can see you can also have this network of bright features. So do you see around each sunspot you have these bright features? Can you see that?
Yes. Yep.
And you see that actually the white, so this is the explanation. When you have more sunspots, you have more faculae. The faculae are bright. So you can see, in particular this one, around that sunspot, you can see lots of bright. So the more, in general, when you have more sunspot activity, you have more faculae activity. And so then TSI increases, even though each sunspot group actually reduces TSI. Does that make sense? Do you now understand why we have these two conflicting theories? Does that make sense? Yeah?
Yeah, I had never seen that image. It's very interesting with the all the white or the brighter areas there. I had never seen that.
Now, here's the next point, and this is something that is not widely appreciated. Like, within the TSI community, everybody is familiar with this aspect. But, and they say, oh yeah, it's because there's more faculae. Okay, that's well known. But notice that there's a lot of bright features that are outside of the sunspots. And do you see all of that?
Yep.
This bright network. Can you see anything here?
Nope.
Can you see anything?
Nothing.
Consistent with that? Nothing. Like, if you're just looking at sunspots, there's a lot of the sun that you're missing. Do you see that?
100%. Yep.
Yeah. So we don't actually know what the relationship between faculae and sunspots, how constant that is between cycles. We don't actually know that. And that's a separate debate that we need to investigate. So now let's go back to our presentation slides. So if we go back here, so one of the groups that was doing is like, well, the problem is you have only one satellite, the Akron, and Akron 1 only lasted, 10 years. So here's the thing. This is the problem. This is each of the satellites that were available for more than a few years, from 1978 up to the mid-90s. You can see here, Nimbus 1 covered a good bit, but you have Akron 1 and Akron 2, and some of you may have heard what's called the Akron Gap. Unfortunately, do you remember I remember it, I guess you remember it as well, the USS Challenger tragedy. That was like, I remember watching that on the news. It'd been heartbreaking. So it was the space shuttle, I think it was 1986, the space shuttle went up and it blew up in just after launch. And everybody wanted to know what was happening. And they said, until we figure that out, there's got to be a hiatus on any space missions. So they were supposed to launch Akron 2 before the end of Akron 1, but they couldn't. So we have, in between, we have this one. This is only recording twice, once every 2 weeks. So that's it. So how do you get these together? So the Akron team, this is NASA's Akron mission. You can see they were one of the main ones. They said, let's try and you can see they show similar patterns. They're following the cycle. Let's try and stitch them together and form a composite. So what they did is they did a composite of Akron 1 and Akron 2 and using Nimbus 7 to fill in the gaps. And because this was only twice a week, they said, we'll just focus on those 3. And this is what they found. So they found this was a big shock. Remember, we said, here's the point. Every solar cycle, sunspots reach 0. The exact same value. You can't have less sunspots than 0, right? Well, they found that when they stuck it together, that each time it went to a different value. The TSI reached a different value. So something is happening. Essentially, the ratio between sunspot numbers and TSI is not constant between cycles. That's what they discovered. That there are intercycle changes in TSI that are not captured by the sunspot numbers. So you can see, like, it kind of goes up and down, up and down. There is a similarity, but there is key difference here. And also, they have, like, there's differences in the maxima as well. So the sunspot numbers is a proxy that's capturing some of the things. Now, I've spoken to Hoy, to the Akron team. They've been co-authors on a couple of papers. And everyone's like, look, maybe that spike is real or not. We don't know. They're like, that's what the data says. But you can see, so maybe that's an artifact or maybe not. Maybe it's real. Anyway, this is the thing. They're saying, look, there's differences, right? Do you see that? Have you seen this before?
Nope, I never saw this before.
Okay. Now, the Akron team have been talking about this for decades, and they've been writing more and more papers, and every time they shout it down. I was like, okay, but if you go back to the papers, you'll see this is what they're saying. This is the point, saying, yeah, there is a relationship between, this is monthly, between TSI and sunspot numbers. It can explain roughly 50% of the monthly variability, but some of that is unexplained, and it's not explained by sunspot numbers. And that's the key. That's why Hoyt and Shatton were saying, we need other proxies. And that's what Akron have been saying. We need to get more proxies. But here's a group that said, no, we don't. So this is the team with the PMOD group. So my German pronunciation, Physikalisch Meteorologisches Observatorium in Davos in Switzerland. So it's PMOD for short. So Professor Klaus Frohlich was the head of this. He died the year before COVID. He started this rival group, and he teamed up with Judith Lean from the Naval Research Laboratory, NRL. We'll hear more about her later on. But they decided they would come up with a new reconstruction, satellite composite. It's called the PMOD. They use a lot of the same data. They use the Akron satellites, but they applied adjustments. And what did they do? They found, wow, when we've applied our adjustments, we've gotten rid of that pesky intercycle variability. So look, TSI flat, just reaching almost the same value each time. Isn't that wonderful? So remember, Akron was saying, actually, we have 3 theories. Akron would say theory 1, TSI decreases sunspots, or sunspots decrease TSI. Theory 2, more sunspot activity means more TSI. But theory 3, there's independent behavior in between. So they were correct. And that makes a complex mess that we've been talking about. PMOD have gotten rid of that. Don't worry about it. Sunspot numbers are magic. And so, in fact, they don't say this, but an implication is that those satellites that cost hundreds of millions of dollars, this, according to PMOD, they're kind of a waste of money, because Galileo, with his little telescope, he was able to record most of what you got. So that's the aside. But also, they managed to flatten out the maxima as well. Isn't this great? Brilliant. Okay, so now they can explain the monthly variability, can explain 60%, nearly 60% of the things. There's some, so you need to add in a few faculae. So they put in, you need a little bit of this sprinkling of this ingredient and that ingredient, but your main base ingredient is sunspot numbers. So remember that, and that's why PMOD proves it. Okay, so is it better? Is PMOD a reliable one? Well, like, first of all, what's the motivation? So this was a nice interview that my colleague Willie pointed out to me. It's an interesting comment. This is a 2003 for a NASA website, interviewed this Akron PMOD debate, and they asked Dr. Judith Lee, well, what do you think? She said, why did you say that? The fact that some people could use the Akron data as an excuse to do nothing about greenhouse gas emissions is one reason we felt we needed to look at the data ourselves. Since so much is riding on whether current climate change is natural or human-driven, it's important that people hear that many in the scientific community don't believe that there is any significant long-term increase in solar output during the last 20 years. Okay, now you can read the full context. That's pretty much it. But if there is that link, Earth Observatory. Just if you Google under variable sun, that's an Earth Observatory that hopefully you can find that. We do give a link to it, but that's fine. It's a motivation. But one of the things I'm concerned about as a scientist is I'm always concerned about what are my confirmation biases? What am I expecting? So there is a concern. I have a concern, and quite a few of my colleagues have concern, that because they were motivated for a particular reason, maybe that influenced maybe even unconsciously, they might, so, but what about the actual adjustment? So the Akron team reached out to Doug Hoyt, who was the head lead scientist at the Nimbus 7 satellite, and said, what do you think of their adjustments to your data? And he wrote this email. It's like, you can find this, you can find the full text online, but Hoyt has said, no non-physical change for that, inconsistent, there is no justification. They looked at every one of the adjustments that they were doing and said, utter nonsense, just there's no basis for this. Physically unrealistic. So that's for the Nimbus 7 adjustments. And of course, the Akron team, they said, no basis for the adjustments that they did to the Akron data. So the PMOD mostly used Nimbus 7, Akron 1 and Akron 2. And then from 96 onwards, they used Froelich was involved in another satellite. So they're using it. So 3 adjustments, the 3 records that they applied adjustments to, the science teams involved in them said, no. So I'm not impressed by that. But actually so you may have heard, you'll hear on the internet, the Akron PMOD debate. But actually, the reason we have this new paper is we discovered that there's new debates that are going on. And what we're dealing with here is since in the 70s and 80s and early 90s, there was a limitation to the amount of satellite data available. Here we have another problem. It's a good problem. We have lots of data. So that's a good thing, right? Except here's the problem. So these, if we look at this, this is Froelic's was the lead investigator on this. This is on the Soho spacecraft, PMO6. And you can see the green line here. But you see the Akron 3 satellite. Do you see the blue peeking up at the top? Can you see the little blue? I don't know if you can see that.
Yeah, I see it.
At the end of the Akron 3 record, the blue is peaking out below. So what's happened is that the Akron 3 showed a greater decline than the PMO6. The source, Tim, started out below all three. By the end, it was above all three. So source is actually going the opposite divergence. So Akron 3 is going down more than the others. Source is going up more than the others. And then here's this other one. Soho, Soho is a nice one because the spacecraft, they decided, actually, let's put 2 instruments. I actually put 4. So each instrument has a main primary instrument and then a backup one that they only takes measurements once a week or something like that. So because of that, they close as your shutter. So they're able to do on-site calibration to see if there's any drips or anything, any problems with the instrument. So Akron did that. So the Diarad and PMO6. This Diarad is on the same spacecraft as this PMO6. So these 2 instruments are physically on the same instrument. And they actually are showing slight different trends. So if you actually look here, it's hard to see on this scale, but if you look at the minimum here, the minimum there, this is actually slightly higher. Source shows the minimum there, this is actually slightly higher than that one. PMO6 shows that this minimum is slightly lower. Okay, so the PMO6 is showing that there's a slight decrease in the TSI between the 2 minima. Diarad is showing a slight increase between the 2 minima. What PMOD do is they say, why don't we average the 2 of them together? We call this Virgo, Soho Virgo, and that way there's no difference between the minima. So that's what PMOD did. That's what Froelich came up with this genius plan. So he's managed to do that. But we have on the same. So that's a problem, right? If we're looking at intercycle, these are the key bits. What's happening between each cycle? Because we have this 11-year cycle, but we also have changes in between. So finally, to our paper. What we've done, this is in Astrophysical Journal, and multiple new or updated satellite TSI composites. And I should say that Professor Scafetta, who I think you've talked to, but he's from the Akron team as well. So he was involved in this. What we did is we took these are the current TSI composites that are up to date. But we noticed that there's actually 4 that have been discontinued. And in particular, there's the Akron and PMOD. So the Akron mission, the last Akron mission ended in 2013. That was the last. And then they ran out of funding, and there were other groups. And also, Wilson he's quite elderly now. He was semi-retired at the time. So he's written quite a few papers, including ones with us there. The Professor Froelich, he passed away in 2019. So the Akron and PMOD groups, that debate is now gone, those groups. But there's the new people at PMOD, they developed a new composite, and there's also 2 other groups that have started. And then Professor Scafetta and also Dick Wilson, Dr. Wilson, they decided, maybe we could do a little compromise where you just update using these other groups. So without comment, this is not the following the Akron methodology, but they're just saying so people can continue doing it. They said, let's just average together these other composites for the post 2013 period. So we said, well, can we do better? And turns out, yeah, we can, because we had all of this extra data. So what we did is we developed I think, is it 21 new or 17 new composites. And we also have the 4 existing ones, all updated to 2013. And then what we did is we ran statistical analysis to try to group them, because 21 is too many. So we got them, grouped them into common groups based on statistical patterns. And what we find is there's 6 different estimates. So we provide all of these estimates to the community. You can use them. And essentially, the PMOD is composite. The old PMOD is composite A. That Akron update that you might have seen is composite C. But we also have these other ones. So we now have 6 different groups. I'll just talk a little bit about which ones are which. Composite, it works out. We didn't group them together this way. We let the statistical algorithm identify the common groups, and you can look at the details in it. But it turns out that composites B and C are all of the ones where we got the Akron composite up to 2013, and then we used different combinations of the more recent satellite data, and you end up with different updates depending on, do you use PMO6, do you use Diarad, do you use Virgo, and you get different results. And so you end up with slightly different ones. So this one shows a greater decline. I don't know if you can see, but you get the solar minima rises, then it falls, and then it falls. And actually, it's fallen back to about the same level it was in the 80s, whereas composite C rises, falls. But it's actually, if you draw a straight line through, this is still slightly more or higher than in the 80s. These ones, what we did is we prioritized the most recent records, missions, but we picked a different satellite mission to prioritize. We said, if the Diarad is most reliable, then let's use that, and then use Akron for the back. And so these end up with different reconstructions as well. So essentially, if I were to pick them, do you remember I was saying that Akron 3 showed a very sharp decrease from the cycle, from one cycle to the next? It's a bit of an outlier. So even though Professor Scavetta might disagree because he is on the Akron team, personally, I think that the Akron 3 might be the less reliable, but I don't know. So I would favor D, E, and F. Composite A, which the IPCC might like, that uses all of the ones that use the PMOD adjustments, they in composite A. And then there's the Belgian group. What they did is they removed, they shortened a lot of the records to be less than one cycle. So I would say composite A is the least reliable, in my opinion. But again, others might disagree. That's the point of science. You don't have to agree. So of these 3, I think they all could be plausible. But I think it's worth pointing out that D and E partially use Professor Froehlich's PMO6 record. Now, he also applied adjustments to his mission as well. And he's passed away, so I don't want to, it's not good to, he can't comment on it himself, but I'm a little bit wary of it. So I, especially since the diarad was on the same one. So I think that this one F, it's the one that maybe it's the correct one, but like you can see, like, I don't know, Tom, can you pick? What do you think? Can you?
I like F, of course, but yeah, I'll defer to you for sure.
No, but it doesn't matter. It's like it does matter. But this is the key bit. We don't actually know. We don't know. And so all of these are available. But that's the thing. Until this paper came out, essentially you had composite A, the equivalent. And then composite C. You're 3 up to 4 and like composite A. And 1 is like, because that was it. And, I don't think we can do that. And so let's just zoom in on this. I don't want to so let's just compare group A. And I've taken the sunspot numbers. This is monthly sunspot numbers. And I scaled them to match TSI for the first cycle, first 12 years. Okay? And you can see, according to group A, that still works. Look, do you see the way that they can rise and fall? So according to group A, that has had all of those adjustments, you get a good match. When we do the same to group F, look what happens. Can you see there's a divergence between them? Mm-hmm. So what that's saying is that if group F is correct, that there is a multi-decadal changes in TSI that are not being captured by sunspot numbers or any of the sunspot number-like ones. As in, the TSI for each minimum is different than the one before. And the same, by the way, applies to groups B, D, C, and E as well. And let's get back to, so if you recall, we had the Mattis. So remember Judith Lean, Dr. Lean, she was involved in the PMOD group. She also is involved in these TSI reconstructions. And so it's called the NRL Naval Research Laboratory TSI, even though I think she's now working, or I think she recently retired, but she had moved to Boulder, Colorado. But they still call it NRL TSI 2. And you can see the black line is that proxy reconstruction. And you see it matches perfectly, right, to group A. So there you go. Wonderful. But if group A is wrong, well, then we're in a problem, right? And because can you see that the TSI is diverging from that proxy reconstruction? Now, remember I said the IPCC used Mattis et al. So Mattis et al. Was 1/2 was this NRL. They got the average of NRL. The other reconstruction was of the satire group. Remember the satire group? This is MPS groups, Max Planck Institute. They said, yeah, so that's also satire S. Now, satire S is the satellite component of their satire models. By the way, they chose the name satire. So for me, maybe it's because like I from Ireland, I'm from Jonathan Swift territory. So for me, satire is describing something satirical. But they like that name. They're still going with it. So this is and it's taken seriously by the IPCC. In fact, the Mattis reconstruction, 1/2 is NRL and the other is satire. So this is interesting. I don't know if you can see it here, but even the PMOD or the Group A, actually with satire, they show a decrease in TSI. They actually disagree with the PMOD. They show that TSI should have been decreasing more than the satellites say, even than PMOD will say. So they actually get a decrease there. And in fact, the NRL, the Judith Lean, has criticized the satire model as being unrealistic because it diverges. They say, oh, it's not good. So there's bickering between them. But again, Matt has said, let's just average two together. Fine, okay. But look at this one here. If Group F is correct, and you can see the others show it doesn't work, but if Group F is correct, the satire says TSI has been decreasing between each minima, whereas Group F says it's been increasing. So if that is correct, then we're at completely opposite behaviors and changes in TSI. So now let's get back, and we're don't worry, we're nearly wrapped up. Let's think about the implications. So if we look at satire, these proxy-based reconstructions, and a lot of them use sunspot numbers, particularly from 1700 or 1610 on, they're predominantly using these sunspot numbers, and they might add in a few extra. Satire adds in an extra, like some other things. If you look at here, you can see the yellow is the satire proxy reconstruction back to 1850, and the red is the Group A. Can you see the two of them overlapping? And you can see, yeah, it kind of is similar. There is that divergence we talked about earlier, but you could say, yeah, it's reasonable. You can see why people are saying, oh, these proxy reconstructions, they match the satellites. They're reasonable, not perfect, but okay. But what if Group F is correct? Well, now we have a problem, right? Do you see that? So if Group F is correct, and by the way, if groups B, D, E, or F is correct, then there's a problem. But if it's F is correct, then there's a major problem. Something is missing from that. And then let's just take one of the other ones that was recognized. So remember, these are the recent reconstructions. So again, Group A, and this is the MU16 Egorova et al. Reconstruction. And you can see here, if Group A is correct, well then that reconstruction is nonsense. Yeah? Because like, the satellites are saying it's flat and this one keeps going up and up. But if Group F is correct, well actually, maybe it's not so bad, right? Still not perfect, but so I don't know. Do you see that what I'm talking about?
I do.
No. So that's the implications of our new paper. So our new paper, and I encourage you. And by the way, I did a video explaining in detail just on the paper itself. So but I wanted this presentation, I've given more background. And so just a quick thing of what's next. So this is some of the projects that we're working on now. So just to say that our Dutch rural record, it was based on version 3. For version 4, no one decided they didn't care how urban they were. They abandoned that. So we're working on developing a new data, but we've also shown that you can't rely on this homogenization. So we're looking at collecting station histories as well and metadata. In terms of the TSI, I think we now, in light of this new paper, do you agree? We have to go back. First of all, we have to look at all of those 41 reconstructions that we talked of, that we'd identify, and we've got to see what ones are actually working, what ones aren't, or is there anything salvageable in them? I think there is. Like we saw that one, that Egorova one match quite well. Some of the older ones seem to match quite well as well. So maybe the older ones were actually better. But I think it's also time to start looking for for solar proxies that are capturing intercycle variability. Everybody's been obsessed with these ones that just focus on the sunspot numbers, the ones that reach zero every minimum, or reach that. We have to find, if we want to take this seriously, to go further back, we need newer data. And that's just related to the topics we discovered today. But I think we should, I just say, we're doing lots of other work. Weather balloon analysis, or we could do a whole talk on each of these as well, or a whole presentation. This one probably wouldn't work for us because if on YouTube, YouTube only does not like you to talk about science that doesn't fit with certain scientific results that don't agree with certain statements that they have decided. And so probably we couldn't talk about that on YouTube, but maybe, that's it. So if you want to, if you like what we're doing, we rely on series. We rely on series named after the goddess, Roman goddess Ceres. If you we could get the name cereal crops from Ceres. That's the origin. So if you've had breakfast cereal today or this week, then you can thank Ceres, the goddess. But we're the modern. Okay, so we rely on donations. So if you can support us, even $10, $100, or whatever or if you can't afford, then share our work, and you can follow my research. You can go to my personal website, RonanConnollyScience.com. You can also find SeriesScience.com. You can also find me on X. So these different handles. One Ronan Connolly on X, Ronan Connolly Science on YouTube, Rumble, and then I was able to get Ronan Connolly on all of those other ones: Telegram, Substack, Blue Sky, Truths, Minds, Parler, all of that stuff. Okay, so I think that's it. Right. So.
Okay. All right. And then I did put links in the show description too, because you have your YouTube channel and you have a YouTube video just on this, so people can click on that if they want to. Any other points?
Hoping to do more as time goes on, more videos. We just launched it there. Yeah. Sorry.
All right. Any other points you'd like to make before we do wrap this one up?
Well, I didn't. Why don't you? Do you have any questions or comments or?
One major one is there any sort of dynamic as you dig into this more and more that the more we learn, the more you find out that everything is more complicated than you thought it was? Is there anything about that? Or
100%. 100%. Let me see if I can find this nice quote that I have. If I can do this, I can share that I think sums it up very well. John Wheeler, who's an American physicist, he said, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." And I think he was correct on that. Does that make sense?
It does. Very good.
And so yes, definitely. The more we learn, the more we know, and the more we know, the more we realize how little we know. That's what I found. But it's fascinating as you learn up. It's like those paradoxes. For me, that's the most exciting thing about science. That stuff about the sunspots at TSI.
I mean, there is this whole narrative that climate is so simple that even a kid can understand it. And if you don't agree, then it's because you're old and you're going to be dead before the bad times hit and you hate kids. Of course, it's all baloney. You probably saw this. I think it's from Jim Steele from 2023. 34% of the world's weather stations have experienced 70-plus year cooling trends. Do you have any comment on that? That blows my mind.
Yeah, well, like the problem is a lot of those stations. It depends on how you count them. A lot of the stations, most of the stations in GHCN version 4, about half of them are like 40% are actually from one region, the contiguous United States. And definitely there's a huge lot of the contiguous United States show a cooling since the 1930s, the Dust Bowl era. So definitely it. I would say the problem that we've been finding is finding enough rural stations that have a continuous 70-year record. That's been a big problem for us. So yeah. So it depends on which data set you are using, how you can do it. But yeah, like definitely for the US, contiguous US, that sounds correct about something like that.
And I'm just looking at the graphic that Jim put up there with that. And for some reason, the cooling stations, they're blue and they're heavily concentrated in the Southeast US. Do you have any ideas what's going on there?
Climate change. Yeah, no, you do get climate change. No, that's the point. That's what we were saying. So you saw that our rural record shows warming, cooling, warming. Now that's average for the full hemisphere, but again, you have the regional variability. But the point is, what we are saying is that the climate is changing. This is why when you hear people saying that they're so-and-so is a... So I've heard somebody say, oh, you're a climate denier. Okay, so how do you deny the climate? Is that like you go out when it's raining without an umbrella? Is that denying the climate? No, they say, oh, no, climate change denying. It's like, half of our papers are studying climate change. Saying, oh, no, so it's you're saying that that humans are doing it. So that's not denying. That's like trying to investigate what are the causes. So somebody that's saying a climate change denier for somebody that is saying, hey, could we consider all of the factors? That doesn't sound to me like denying. That sounds like, can we look at it? It sounds like the person saying denier is in denial about something. You can find me on the various social media, RonanConnollyScience.com. You can find you can find the links to the different ways to contact me and to look at our work. And again, please donate to the series if you like what we're doing. Of course, if you don't like what we're doing, that's it. And if you can't afford it, or you don't share our stuff, tell people, let people know, and that's it. Okay, thank you, Tom.
All right, Ronan Connolly, thanks a lot for doing this. You are a super interesting guy, a very interesting family overall. So thank you for doing it. We'll talk to you next time.
Thank you.
Goodbye.